It is a little after 11 at night. You are on a two-lane road somewhere in the middle of the country, the kind of road with no streetlights and a center line that vanishes every few hundred feet. Off to your right, out in the dark, you notice lights. 3 of them, one high, 2 low, arranged in a shape you have seen 1,000 times and never once actually looked at. A triangle. You slow. The gates come down. 40 seconds later, 400,000 pounds of locomotive crosses the road in front of you at 50 miles an hour. Here is the part almost nobody knows. The bright one on top, the headlight, the one throwing a beam a quarter mile down the rail, is not the thing that saved you. It was the 2 dimmer ones underneath. And the strangest fact about those 2 lights is that they were not invented to be seen. They were invented so that a man in a cab could see something else entirely on a mountain railway in Western Canada for reasons that had nothing to do with roads or cars or you. So how does a piece of equipment designed to stare sideways into a drainage ditch end up as the most recognizable safety signature in North American railroading? To answer that, you have to start somewhere uncomfortable. Your eyes are terrible at judging an approaching train. Not slightly unreliable. Systematically, predictably wrong in ways that have been measured and documented and that have not improved at all in the century and a half since railroads and roads first started crossing each other at the same level. The trouble begins with geometry. When a train is on a course to reach a crossing at the same moment you do, it holds a constant bearing in your field of view. It does not sweep across your windshield the way a car on a side street does. It sits there, roughly in the same spot, getting larger. And human vision is built to detect movement across the visual field far better than it detects growth within it. A thing that slides catches your eye immediately. A thing that only expands can hover at the edge of your attention for a very long time before anything in your brain flags it as urgent. Then there is size. Large objects appear to move more slowly than small ones traveling at the same speed. Anyone who has watched a wide-body airliner drift down toward a runway has felt it. The aircraft looks like it is floating. It is doing 150 miles an hour. A locomotive triggers the same illusion in the worst possible circumstance on a driver who has 30 seconds to decide and who has crossed these particular tracks 400 times without ever meeting a train. And at night, all of that gets worse because at night, you are not looking at a locomotive at all. You are looking at a single point of light. A point of light carries almost no information. It has no width for you to measure, no edges to compare against a fence post or a tree line, nothing that visibly grows as it closes. It is bright, and then it is brighter. And brightness is a miserable cue for distance. Ask anyone who has misjudged a motorcycle at dusk. One lamp in the dark could be half a mile out, or it could be 400 feet, and the human brain, doing its best with what it has, will guess. Frequently it guesses that there is time. For roughly 100 years, the railroad industry's answer to this problem was to make the point of light brighter. The first headlight in American service was not a lamp at all. In the early 1830s, on one of the earliest common carrier lines in the country, the solution to running after dark was a fire. Pine knots were burned in an iron basket set on a bed of sand, riding on a flat car pushed ahead of the locomotive. It threw sparks, it threw smoke, and it was better than nothing, which at the time was the only competition it had. Within a decade, the improvised fire gave way to something recognizable. By 1840, a New England railroad was advertising a very bright headlight with powerful reflectors, mounted on the front of the engine so that freight could move at night. That sentence contains the entire commercial logic of railroad lighting. The headlight was never primarily a safety device. It was a device that let a railroad use the other 12 hours of the day. Oil lamps followed, then kerosene burning inside a polished reflector in a box the size of a footlocker. Then, near the end of the century, electricity. Arc lamps drew a continuous spark between 2 carbon rods and threw a light so much stronger than anything before it that crews on the plains suddenly stopped hitting livestock at night. Incandescent bulbs rugged enough to survive a locomotive front end arrived around 1913. By then, more than 30 states had written headlight requirements into their own laws, and in 1915, Congress made electric headlights a federal requirement nationwide. That was the pattern for the next 80 years. More candle power, better reflectors, sealed beams. By the modern era, federal rules would settle on a headlight producing at least 200,000 candela, aimed to illuminate a person standing at least 800 feet ahead of the locomotive. 800 feet. Think about that number for a second because it explains the entire tragedy of a grade crossing. 800 feet is the distance at which the engineer can first see a human being on the track. A loaded freight train at track speed needs somewhere between a mile and a mile and a half to stop. The headlight was never really for the driver at the crossing. It was for the crew, and even for them it arrived far too late to matter. Railroads knew something was missing. You can see it in the strange collection of extra lamps that sprouted on locomotive noses through the middle of the 20th century. There were classification lights, small lamps on either side of the front end showing white or green, which told everyone along the line whether the train was an extra running outside the timetable or the first section of a scheduled train with another one behind it. That was not a safety warning. That was a message from the railroad to itself, written in colored glass in an era before radio dispatching. And then there was the light that actually moved. In the late 1930s, a Chicago firefighter began experimenting with a lamp that swept its beam in a figure 8. The idea came from the same instinct that puts a rotating beacon on a fire truck. A steady light blends into a landscape of steady lights. A moving one does not. His oscillating lamps and the competing designs that followed ended up on the noses of streamlined passenger locomotives across the country, tracing slow, luminous loops down the right-of-way ahead of the train. Some railroads fitted a second one that burned red and switched on automatically if the brakes went into emergency. They worked, but they were mechanical devices with motors and linkages in the worst possible environment, and they were expensive enough that they mostly stayed on passenger power, where the public was watching. A freight locomotive dragging coal through the dark at 3 a.m. usually got one lamp and nothing else. Meanwhile, the collisions kept happening at a scale that is hard to believe from where we stand now. In 1972, the average number of collisions between trains and highway vehicles at American grade crossings was running above 12,000 a year. 12,000. That is more than 30 a day, every day, and it was steady enough that people in the industry had stopped treating it as a crisis and started treating it as weather. That same year, a governor's office in Idaho, the state peace officers, and a railroad put together a 6-week public education campaign about crossings. Fatalities in that state dropped by 43% in the first year. The campaign spread to Nebraska, then Kansas, then Georgia, then everywhere, and it is still running today. It proved something important, which is that a meaningful share of these deaths came down to what the driver understood in the last few seconds, which raised an obvious question. If the driver's understanding is the weak link, could you build a locomotive that explains itself better? Now we go north, and this is where the story turns, because the answer arrived from a direction nobody was looking. In the mountains of British Columbia and Alberta, one Canadian railroad ran a line through country that regularly tried to kill it. The route between the Rockies and the Pacific coast threaded terrain where rock came down onto the right-of-way without warning, where slides could put a wall of debris on the rail around a blind curve, and where a headlight aimed straight down the track told a crew almost nothing about what was sitting just off the railhead waiting. So in the early 1960s, crews on that territory started running with a pair of extra lamps mounted low on the front of the locomotive, angled outward, not down the track, off to the sides, into the ditches. They were literally called ditch lights because that is exactly what they were for. Early ones were removable, fitted for the mountain run and taken off afterward. They gave the engineer a wash of light across the shoulder of the roadbed, the cut faces, the drainage, the places where trouble collected before it reached the rail. It was a purely operational tool, invented by railroaders for railroaders, and its entire purpose was to buy a few extra seconds of warning for the men in the cab. Nobody involved was thinking about a driver in a pickup truck 3 provinces away. But in solving their own problem, they had accidentally built the answer to somebody else's. Because 2 lights mounted low and wide, combined with 1 light mounted high in the center, make a shape. And a shape is a completely different kind of information than a point. A single lamp gives your visual system nothing to work with. 2 lamps separated by several feet give you a baseline, and a baseline can be measured. As the locomotive closes, the angle between those 2 lower lights widens, slowly at first, and then with increasing speed. And that widening is something the human brain reads well without being taught. It is the same cue that lets you judge an oncoming car by its headlights. The triangle adds a 3rd reference above the pair, which gives the pattern height as well as width, and critically makes it unmistakable. Nothing else on an American road at night is arranged that way. Not a truck, not a motorcycle, not a farmhouse porch light 2 fields over. The pattern does not just say something is coming. It says a train is coming, and it is coming this fast. American regulators had been circling this idea for years without landing on it. Government researchers ran studies through the 1970s on oscillating headlights, rotating beacons, ground lights, and roof strobes, and found repeatedly that two auxiliary lights in a triangular arrangement with the headlight out performed everything else. Rulemaking was proposed in 1978, again in 1979, again in 1982. Each time comments came back, questioning cost, reliability, and real-world effectiveness, and each time the effort was dropped. Then, in 1991, the research restarted in earnest, and in 1992, Congress removed the option of dropping it again, directing the Secretary of Transportation to finish the conspicuity work and issue rules. What followed is worth walking through, because the numbers are specific. 2 locomotives were fitted with 3 different auxiliary light systems at once: roof-mounted strobes, ditch lights aimed 15 degrees outboard, and crossing lights aimed straight ahead and flashing. Each pair formed a triangle with the headlights. In November of 1993, observers were positioned at a simulated crossing in daylight and in darkness, and asked to do 3 things: watch, notice the train in their peripheral vision, and estimate when it would arrive. Every one of the 3 systems beat a plain headlight. The average detection distance with headlights alone came out around 1,250 feet, with ditch lights roughly 1,390, with flashing crossing lights about 1,550. Convert that into the currency that actually matters. At 25 miles an hour, a driver with only a headlight to look at had about 34 seconds. A driver looking at the crossing light triangle had about 42. 8 extra seconds, produced not by more light but by better arranged light. 8 seconds is the difference between braking and stopping. Alongside the perception work, 3 railroads ran the triangular arrangement in actual revenue service for 3 years, and compared their crossing accident numbers against the 3 years before. The reductions they reported ranged from roughly 55% to over 75%. Those were early figures from a limited program, not a controlled experiment, and the honest way to read them is as a strong signal rather than a precise measurement. But the direction was not ambiguous. Installing the hardware cost about $2,600 per end of a locomotive in the mid-1990s, which against those numbers was close to the cheapest safety intervention available to the industry. If you are finding this worth your time, go ahead and subscribe. We cover railroad engineering and the reasoning behind the machines every week. The final rule came in 1996 with a compliance deadline of December 31st, 1997. That date is the reason so many photographs from the mid-1990s show locomotives with brackets welded onto noses that were never designed for them, ditch lights bolted on wherever the sheet metal allowed, sometimes hanging off the pilot and housings that looked like an afterthought because they were. The requirements are unusually precise about geometry, which tells you exactly what the regulators believed they were building. The 2 auxiliary lights must sit at least 36 inches above the top of the rail. They must be at least 36 inches apart, and if they are mounted close below the headlight, less than 60 inches beneath it, they must be spread at least 60 inches apart instead. That second clause exists for one reason. A tall, thin triangle and a short, wide one are not equally readable at distance, and the rule refuses to let the shape collapse toward a straight line. Each light must produce at least 200,000 candela, the same intensity standard as the headlight itself, and must be aimed within 15 degrees of the locomotive's center line. Canadian rules go further and specify the aiming exactly. The beams cross the center line 400 feet ahead and strike the rail at 800. They are required on the lead locomotive whenever it operates faster than 20 miles an hour over a public crossing. Both must be working before the train leaves a terminal where its initial inspection is performed. If one fails on the road, it has to be fixed by the next scheduled inspection, and a locomotive that shows up at a terminal with a dead ditch light either gets repaired or gets shoved back into the consist to run as a trailing unit. There is one exemption worth knowing. Locomotives built before the end of 1948 and not used in regular passenger service are treated as historic equipment and are not required to carry the lights. That is why a restored steam locomotive can run an excursion over public crossings wearing nothing but a single headlight, exactly as it did in 1944, while the modern diesel trailing behind it carries the full triangle. Then there is the flashing. Under the rules, the auxiliary lights may burn steadily, or they may flash on the approach to a crossing. If they flash, they must alternate, left then right, at between 40 and 180 flashes per minute, and each railroad has to write a standard procedure into its operating rules for when the engineer uses them. The flashing can be triggered automatically, but the engineer must be able to switch it on and off by hand. In practice, the trigger is usually the horn. The engineer pulls the cord at the whistle post, roughly a quarter mile out, and the two lower lights begin trading places in the dark. In the original in-service trials, the lights burned steady while the train ran, then flashed alternately for 30 seconds after the horn sounded, which is very close to how it still works today. That alternation is doing something specific. A steady triangle tells your visual system what the object is. A triangle whose base is swinging back and forth adds motion to a scene where the dangerous thing is otherwise almost motionless in your field of view. And motion is the one thing your peripheral vision is genuinely excellent at catching. It is why you notice a turn signal in a mirror you were not looking at. Not every railroad flashes. Some run steady, some flash only in certain territory, and a locomotive borrowed from one road and running on another may behave differently from the units around it. Spend enough time at a crossing and you start reading which is which. It is worth pausing on what all of this looks like from the other side of the glass, because the arithmetic in the cab is brutal. An engineer on a night run sees a corridor of light maybe 800 feet long and, at its edges, the pale wash of the ditch lights across ballast and weeds and the reflective backs of signs. Everything beyond that is a black tunnel with two rails in it. He has a horn, an emergency brake application, and no ability whatsoever to steer. When something appears in that corridor, the outcome has usually been decided by physics several thousand feet earlier. So the ditch lights still do their original job. They show the points of a switch, the shape of a washout, the eyes of an animal on the shoulder, a person walking the ties. That job never went away. It just stopped being the reason the lights are legally required, which leaves one uncomfortable gap, and it is the gap the triangle cannot close. The lights are on the front of the locomotive. They warn you about a train that is coming. They do absolutely nothing about a train that is already there. A significant share of crossing collisions, somewhere near a quarter of them, are not vehicles struck by trains. They are vehicles driven into the side of a train that is standing or moving across the crossing already. At night, an unlit string of freight cars is effectively a wall with no surface texture, no light of its own, and no shape your headlights can resolve until you are far too close. Drivers have reported afterward that the road simply appeared to be empty. The answer arrived much later and much quieter. In 2005, federal rules required retroreflective sheeting along the sides of freight cars and locomotives, applied in strips around 42 inches above the rail, with the amount scaled to the length of the car. It has to be inspected, replaced when damaged, and swapped out after 10 years regardless of condition, because reflective material degrades whether anyone notices or not. It is the least dramatic safety system on the entire railroad. No beam, no flash, no moving part. It only works when your own headlights hit it. And that is exactly the point, because the failure it addresses is a driver who has no reason to think anything is in front of him. Put the two rules together and you get the modern grammar of a train in the dark. A triangle at the front that says something is coming and tells you how fast. A line of returning light down the side that says something is already here. So, does any of it work? The number of collisions between trains and highway vehicles in the United States has fallen from more than 12,000 a year in the early 1970s to roughly 2,200 in recent years. That is not one intervention's doing. Crossings were closed and consolidated. Gates and flashing signals replaced crossbucks at thousands of locations. Responsibility for choosing protection at each crossing moved to highway authorities with federal money behind it. Public education spread across every state. The lights are one strand in a rope, but they are a strand you can see. The two dim ones down, low, exist because a crew in the mountains wanted to know what was lying in the ditch before they hit it. They spread across a continent because a set of field tests in 1993 established that the shape 3 lights make is worth more to a human being than the brightness any one of them produces. They are bolted to essentially every road locomotive in North America, doing a job their inventors never imagined, for people their inventors never met. So the next time you are stopped at a crossing at night, watching a headlight swell out of the dark, look at what is underneath it. Watch the two lower lights start trading places when the horn sounds. Watch the base of that triangle widen as the locomotive comes on. That widening is the whole point. It is the machine telling you, in the only language your eyes reliably read, how much time you have left. For a century, railroads answered the darkness by burning brighter. It turned out the darkness was never really the problem. The problem was that a single light, however fierce, could not tell you anything about itself. It took 160 years, a mountain railway, and a handful of observers standing in a field in November to work out that the solution was not more light. It was 3 of them, arranged so that you could finally understand what you were looking at.